Okay, today we're going to talk about pointers. And pointers are really just address types. And all the address data types, they don't hold domain values, where a domain value is a piece of data from the domain that our program is modeling. So for example, if our program is being written for an accountant, then the domain values might be accounts, receivables, credits, debits, etc. Instead, address types hold the address of things in memory. And usually these things are other variables, but sometimes they hold the address of functions as well. So why do we have address types? Well, it makes moving data more efficient. So we've already seen a reference parameter. That's an address type. This made it easy for us to pass a large piece of data to a function without having to create a copy of the data. These address types, though, they also allow us to build complex data structures, and that, of course, is the focus of this entire course. So the main type of address variable that we'll use is called a pointer. And a pointer, again, is an address address variable that tells us where to find something, basically. Okay, so we could do something like this. To declare a pointer. Okay, so we have three things going on here. First, we have, this is the type of data that we want the pointer to point to. If you can declare a piece of data, you can have a pointer to that type. So it can be an int, can be a float, can be a student, any valid type. The star indicates that this is a pointer and not an int or a float or a student. The star says this is a pointer. So unfortunately there is no pointer keyword. We use this star next to a data type to indicate that we want a pointer. And then lastly we have the ID or the name of the pointer. Okay. Now, the ampersand character is called the address of operator, and that's going to be important here in a second. Okay, so if you have a variable, you can put this ampersand in front of it to get the address of that variable. So let me do another example here. Okay, so I'm going to create a piece of data, in this case an integer. And of course, when the flow of control gets to this point, that means go carve out room for this box called num, and we're going to assign an initial value of 1,000. Okay, but on the very next line, if I do this, I'm going to create an int pointer called pnum. Okay. So when the flow control gets here, this says go carve out room for a pointer, and we're going to call this pnum. Okay, the next thing we'd want to do is we need to assign the address of the variable called num to be stored inside the pointer called pnum. So the way we would do that is say pnum is equal to the address of num. Okay. Now, each one of these variables, of course, it has an address somewhere in memory. So let's say, this numeric address just happened to be, 576. Right? What this line says here is take the address of num, which happens to be 576, and store it inside pnum. Okay. So all pointers are really just integers. They hold the integer value of the address of another variable in memory. So you might wonder, well, why don't we just declare integers to hold pointers? Well, we're going to discuss why we don't do that. instead, we should be using this syntax here that I just described. Now, the address of operator, the ampersand, is used quite a bit in C++. It's probably overused. So, of course, we know we have the double ampersand, that's logical and. There's something called a bitwise and, which is also a single ampersand. When we have a reference parameter, we indicate that with the ampersand, and now our address of operator is also using an ampersand. So why they didn't mix it up a bit? Why didn't they use some of the other characters on the keyboard? I'm not quite sure, but that is the syntax. Okay, so the other thing about pointers, okay, they hold the address of things, but what one would want to do is dereference a pointer to get to the pointed to data. So to dereference a pointer, we use the star and then the pointer name. The star is probably overused, I think, also. Okay, so in this example here, if we said cout star pnum, okay, that's a dereference. Whenever you have a star right in front of a pointer, this says go to what pnum points to. And I like to think of these pointers as really holding the address of something. So you'll see me draw this picture quite a bit. This says go to what pnum points to and print out that value. In this case, it would be, we would print out 1,000. We'd see 1,000 on the screen. Or, okay, so that's an example of reading using a pointer. We can also write a value. If we said pnum is equal to 2,000, I'm sorry, star pnum. This says go to what pnum points to and write the value 2,000 in that location. Okay, so that actually changes the value inside num, and we didn't use num to do that. We used the pointer to do that. Okay, so let's look at maybe a more complete example here. So this is basically the same program. Here we have a normal integer. We have two pointers called pointer 1 and pointer 2. And then we set num1 equal to 10. And then we store inside pointer 1, we make it the address of num1. Okay. So maybe I can draw this in memory. Okay, so here's num1, and we said num1 has a value of 10. Right. Then we have these two other pointers called pointer 1 and pointer 2. So here's p pointer 1, p pointer 2. And then we set p pointer 1 equal to the address of num1. So this pointer points to num1. And now if we were to see out the value of num1, of course what we'd get is the value 10. If we did a see out of the address of num1, okay, what we would get is the numeric value of num1. If we did a see out of star p pointer 1, that says go to what p pointer 1 points to and print that value out. In this case it would be 10. And if we did just did a see out of p pointer, that would print out the numeric address that's being stored inside here. So again, whatever numeric address, wherever num1 happened to land, that's what would get printed out. Now we can change what the pointer points to by dereferencing it. So star p pointer 1 equal to 100 means go to what p pointer 1 points to and replace the value 10 with the value 100. Okay. And now if I did a see out of num1, of course what I'd get is the value 100 because num1 has changed. And if I see out star p pointer 1 again, we'll get the value 100. Now p pointer 2, I'm setting equal to the address of num1. So what that means is now this guy also points here. Okay. And if I were to dereference star p pointer 2, I'd print out the value 100. And then this is just multiplying the numbers together. This is kind of a joke to see how overused some of these operators are. So the star is used for multiplication, of course, but it's also used to dereference a pointer. So 100 times 100 is 10,000. Okay, so p pointer 1 is 100. 100 times 100 is 10,000. That's going to be stored in whatever p pointer 2 points to, which of course they're right now both pointing here. Okay, and if we were to see out p pointer 2, of course we get the value 10,000. Okay, so let's talk about a little bit more about these pointers. So pointers can point to objects. An object, of course, is a variable created from a struct or a class. And all objects have data members that can be accessed using our dot notation. However, the dot in dot notation has a higher precedence than the dereferencing star. So we're going to have to learn the syntax in order to deal with this precedence problem. Okay, so let's look at this example here. So I have this struct that represents a student. Okay, every student has an ID, a midterm grade, and a final grade. Okay, here I declare a student object, S1, and then I create a student pointer, again, just using the data type and a star, and then we give the name, pStudent is the name of the pointer. Let me draw this one out. Okay, so here's S1 with the ID, middle, final. Okay, now pStudent is again, it's a pointer, it's an integer. It just holds an address. Okay, pStudent is not a student. It is a pointer. It really is just an integer value. Here I put some values inside the student object S1. We have 1, 90, and 100. We of course can still use our dot notation. So s1.id says go find the thing called s1, pull out the ID member. Same for mid and final. Okay. Here's where it gets interesting. I can take the address of s1 and store it inside the pointer called pStudent. Now what this means is this pointer points to this student. Okay, and here's the precedence problem where we want first to dereference the pointer. We want to say go to what pStudent points to. It's an object, and then select off the data member. Without these parentheses, this would not be correct. So notice what I have here. Without the parentheses, the period would have a higher precedence, and the compiler would think that pStudent is an object and we're trying to pull off the ID member. That's not true. pStudent is not an object. It's an integer. Okay, so we first must dereference the pointer and then select the data member. Now there's a shorthand notation because this is kind of cumbersome using the parentheses and then the period afterwards. So we call this shortcut notation, we call it arrow notation. So basically what we can do instead, look at this line here, we say pStudent arrow ID is equal to 3. This says basically go to what pStudent points to and select off the ID member. Now of course this only works with objects and pointers to objects is the only time you'd want to use the arrow notation. Okay, let me show you another example. This is again one with students. You can have an array of pointers. Okay. So here we have an array of 3 student pointers. Then we have 3 student objects, and we assign the address of those 3 student objects to the 3 pointers at 0, 1, and 2. And then if I want to access any one of the students, again, using my arrow notation, this says go pick this is basically the 3rd student pointer, and then the arrow ID says, using that pointer, go select off the ID member and set it equal to 2. Okay, so you can have arrays of pointers. Now, speaking of an array is really a combination of a block of data and a pointer. So it turns out when we're using arrays, we have been using pointers, kind of all along. Okay, so let me draw another picture. Okay, this time I'm gonna make an array of floats. Okay, of course, when we see this, we know exactly what's happening. This says go create an array of 5 floats in memory. Okay, and really 3 things happen. First thing, obviously, we do allocate room for 5 floats. Okay, but another thing happens. We create this pointer called ARR. ARR, the identifier for this array, is really just a pointer. And then the last step is we assign the address of the very first byte of the very first float in the group to the pointer. Or in other words, this pointer points exactly right here. Okay. Now, we also have this thing called pointer arithmetic. It allows a programmer to manipulate addresses. Okay. So since all pointers are just integers, no matter what type of data the pointed to data is, it makes sense that we should be able to do arithmetic with them. Right? So if we said something like ARR plus 1, well, this is just an address, a numeric address, so we should be able to add 1 to it, or ARR plus 2. Okay. So let's go back here and imagine that these bytes from the float, every float is 4 bytes, at least on my machine here. Right, so the address of these 5 floats would look something like this. Okay, so let's just say this happens to be memory address 576. Well, exactly 4 bytes away from that would be 580, 584, 588, 592. Okay, when we add 1 to a pointer, right? So right now ARR holds the address 576. Adding 1 to it will not make the address 577. Instead, it will make the address 580 because a float is 4 bytes on your machine. And the compiler knows what type of pointer we have. That's very important. Specifically so we can say, when we do some pointer arithmetic, it knows how many bytes away to move. Okay. Now, you can use this value to reach any element in an array. So for example, if we said something like this, ARR plus 0, right, that's an address, that's 576, and if we dereferenced that, we could store a value in there. Okay. So really this is ARR plus 0, this is ARR plus 1, this is ARR plus 2, and so on. Okay. So that's what these index values mean, basically. How many full floats away from the beginning of the array do we want to access? Okay. And this is why we don't just use ints to store pointers. Okay, the compiler must know the type of the data that the pointer is pointing to, so it knows exactly how many bytes to move over whenever we do any pointer arithmetic. Okay, so it turns out, like I said, we can use this notation. Right, we take a pointer, we add some value, and we dereference it. Or we could use our familiar array notation. These two things are exactly equivalent. And array notation is really just it's a shorthand notation for doing pointer arithmetic. Okay, so either one is okay. You could, if you want to get to the third element, you could say ARR plus 2. So here's ARR plus the size of 1. 2 elements away, that's this address 584. If we wanted to put the value 20 there. Or we could say ARR at position 2 is equal to 20. Either one is perfectly fine, and they're exactly equivalent. Okay, it's a little bit easier to write the square brackets, so I think most people would probably do that. Okay, but you could do either one. So here's basically the same example here. We have an array of 5 floats, and here I have a float pointer called pCopyArray. So this is kind of interesting. We can set pCopyArray. We can make it equal to ARR. And this code will actually compile. I'm not going to compile it here, but you can compile it on your machine. And the only reason this would compile, or the only way this would compile, is if ARR and pCopyArray were exactly the same type. And it turns out they are, right? Because ARR is just a float pointer. It's a pointer that's pointing to this first float in the group. And we won't get any syntax errors. This is perfectly legal. Then again, we could use either notation. We could do our pointer arithmetic and dereference the pointer, or we can use array notation. And it turns out we could even use array notation with the pointer pCopyArray, since they are exactly the same type. You know, this just does the shorthand notation for us. Okay, let me jump ahead here to program 7, just to point out that when you compare pointers, you're really comparing addresses, not domain values. Okay, so here's a similar program. We have num1, num2, and then pointers pnum1 and pnum2. Okay, and these pointers hold the addresses of num1 and num2, not the actual values. So if we asked, is pnum exactly equal to pnum2, this would be false, because pnum1 holds the address of num1, pnum2 holds the address of num2. Those things are not the same. However, if we dereferenced the pointers, of course this would be true, since both num1 and num2 do hold the value 10. Okay, this says go to what the pointers point to and compare those two values. In this case, they would be exactly the same. Okay, so let's see. We can pass by reference. Is actually very similar to using a pointer. And in the C language, the precursor to C++, there was no pass by reference. There was no ampersand you put next to the data type. Instead, you had to use a pointer to get the same behavior. So let's look at program 5 here. And basically we have a main and this function that is passed in an int pointer, where what we want to do is we want to print out the value that the pointer points to and then increase the value. Okay. So up here we have num, starts out at 10. When we see out num up here, we're going to see 10. And then when we call the function, what we do is we take the address of num. Okay. So the address of num is the numeric address in memory where the variable num happens to live. And we're going to pass that down to be stored inside this pointer called pint. And when we dereference pint, that's going to, again, print out the value 10. When we increase the value, this says go to what pint points to, which is that variable called num. and we're going to add 1 to it. It's going to go from 10 to 11. Okay, when the flow of control returns back to main, okay, num's new value is going to be 11 because we passed a pointer down to the function and we dereferenced the pointer. That is exactly the same behavior we would get with a pass by reference parameter. Okay, let's see what else can we do. There's a special value for pointers called null, and that means the pointer does not point to anything. Okay, and the null value is the value 0. So if you want to assign a null value to a pointer, you're going to store the value 0 in there. If you dereference a null pointer, your program will crash. So let's look at program 6 here. Here we have a null pointer. I declare an int pointer called pint and I set it equal to null or 0. And then here I try and dereference a null pointer. And what's going to happen here is your program will crash exactly here on line 11 every single time. So the cout that comes on line 14, we will never see that no matter what, because whenever you dereference a null pointer, the program crashes. Now, if you're using Visual Studio and you're running the program and you dereference a null pointer, you'll get this gray window that pops up that says basically you dereferenced a null pointer, and it will even go through this process of trying to find a solution online. I think we've all seen these windows before. If you're compiling from the command line or you're on a Mac, the program will crash, but it won't give you this pop-up window. Okay, you just won't see the hello world part. Okay, another bit of code that might cause your program to crash is to use a pointer that does not have a valid address in it. So every running program lives in your computer's memory, and we call a running program a process. A process image stores all the compiled instructions to execute, a record of where the flow of control is and should return, and room to store all of your data. All of this is grouped together into this thing called a process image. Okay, and every single program that's running, there is a process image in memory. So if this is your computer's memory, you might have maybe a web browser running, maybe a word processor, and maybe some IDE. Okay. Each one of these programs occupies a certain amount of memory. Okay, since each process image is in memory, each one has a starting address and an ending address. Right, so here's the start of this process image, and here's the end. These are numeric addresses. If a pointer in one process attempts to dereference an address that's in another process, the operating system will kill the offending process image. In other words, if your browser has a pointer in it and it tries to address something that's outside the bounds of the process image, right? Again, these are just numeric addresses, these pointers. So if there's a pointer in this program that points somewhere outside the process image and we try and dereference it, the operating system will kill that program. And this is one of the fundamental things that an operating system does. It prevents a misbehaving program from affecting other programs. So if somebody writes a bad browser with this really buggy code that has these pointers that are pointing to this memory that's outside the process image, the operating system will say, no, you can't do that. The operating system monitors every single memory reference, and will kill any process that attempts to access memory that does not belong to it. Okay, this is relevant to us because we may declare a pointer but forget to set it. So for example, we might have, let's say we declared a float pointer called pnum. Right? And pnum right now holds a garbage value. okay, because I haven't set it. Right? If I now dereference that pointer, okay, what's likely to happen if this value is some garbage value, let's say it's some gigantic value, it's probably going to refer to some chunk of memory that's outside the process image. Okay? And this is going to cause the program to crash. Okay, so if, like I said, if we do this, then we're likely outside the process image and the program's going to crash. When a pointer holds a value of 0 or any address outside of the process image, and we attempt to dereference it, our program is going to crash. And unfortunately, this is going to happen to all of you because we're going to be doing a lot with pointers, and we don't really know how to use them yet. We'll get better, of course, but chances are this is going to happen to you a lot, and your programs are going to crash, and you're going to kind of scratch your head and figure out, well, what did I do wrong with the pointer? That's one of the main things that we're going to learn in the course is how do we deal with pointers.